Welcome back. Episode 3. From Math to Signatures. Today we watch Alice sign a document, and Bob verify it. Then we look at how Ladhe stacks up against the NIST standards, and against quantum key distribution.
Quick recap from Episode 2. The private key is the secret tuple of distinct odd primes, summing to P. The public key is P itself, plus the SHA-256 hash of the encoded compressed witness. Now we use these to sign and verify a message.
To sign a message M with private key P and the primes, Ladhe does three things. First, bind the message to a fresh transcript, using the Fiat-Shamir transform. Second, use the secret primes to construct a witness W that opens the public commitment H. Third, output the signature as the transcript, the witness, and a message tag. About 100 bytes total. No exotic math, no hypertree, no number theoretic transform.
To verify a message and signature against the public key, Bob does three things. First, recompute the Fiat-Shamir transcript from the message. Second, check the witness arithmetically. Components must be consistent with P, and the encoding must be well formed. Third, recompute the SHA-256 hash of the encoded witness, and check that it matches the public commitment H. If any step fails, reject. Otherwise, accept.
An important caveat: Ladhe is a one-time signature scheme. Signing reveals the witness W. Anyone who sees one valid signature learns enough about the witness to forge a different message under the same key. Therefore, one Ladhe key signs one message. For many-time signing, the paper sketches a Merkle aggregated construction in Section 6. The same idea SPHINCS plus uses. That variant is not yet implemented in version 1.0.
Here it is in action. Run Python Ladhe rsa.py demo 5. Key generation produces P, the primes, and the public hash. Signing takes about a millisecond. The signature is 104 bytes. Verification takes about half a millisecond. And tampering with the message produces a clean rejection.
Now the comparison. Here is Ladhe v1 alongside ML-DSA 65, FIPS 204, and SLH-DSA 128S, FIPS 205. Ladhe signatures are roughly 100 bytes, compared to 3,000 for ML-DSA, and almost 8,000 for SLH-DSA. Ladhe public keys are about 36 bytes, compared to 1900 for ML-DSA, but, and this matters, Ladhe is one time only, and has no community cryptanalysis yet. The NIST schemes are many time and extensively studied.
Where does Ladhe win in version 1? Signature size, about 33 times smaller than ML-DSA, and 78 times smaller than SLH-DSA. Public key size, about 54 times smaller than ML-DSA. Code simplicity, no number theoretic transform, no hypertree, about 600 lines of auditable Python, pure software, no hardware accelerator required, and the same security foundation as SPHINCS+.
And we owe you the honest version 2. Where does Ladhe not win in version 1? It is one time only. The many-time variant is sketched in the paper, Section 6, but not yet implemented. Key generation is slow at high bit sizes, around 90 seconds at 3322 bits. It is not NIST standardized. That process takes 5 to 10 years, and there is zero community cryptanalysis yet. That last point is the biggest. Use Ladhe as a hedge alongside an NIST standard, not as a sole replacement.
What about quantum key distribution? QKD and Ladhe are not really competitors. QKD distributes symmetric keys between two parties, using quantum physics protocols like BB84. It needs dedicated hardware, fiber or satellite links, and works only over limited distances, roughly 100 to 300 kilometers in fiber. Each node costs tens to hundreds of thousands of dollars. Critically, QKD does not authenticate. It actually requires a digital signature scheme on top, to prevent man-in-the-middle attacks.
QKD and Ladhe complementary, not competitive. QKD distributes a symmetric key between two endpoints. Ladhe, or any signature scheme, is what proves the right parties are on the line. In a real QKD deployment, you still need a signature scheme to authenticate the classical channel that QKD depends on. Ladhe could play that role. Different tools, often used together. We are not competing with QKD.
We now have working signatures, sized, and compared honestly against the alternatives. Up next, Episode 4, Certificates and X.509. Signatures alone are not enough. Bob needs to know that the public key really belongs to Alice. That is what certificates are for. Thank you for watching.